Most of the universe is playing out in total darkness beyond our sight. A silent, relentless growth is happening right now in the cosmic voids, a process we call the quiet expansion. It challenges everything we think we know about reality. We map the stars and the ancient light from the Big Bang, but a vast part of the cosmos remains permanently hidden behind a horizon we cannot cross. By the end of this journey, you will see the entire cosmos in a completely new light. What strange forces are driving space itself to stretch in the silent dark? And could this expansion one day tear apart the very fabric of reality? How does it feel to look up at the night sky, knowing most of the story is written in the dark? Our cosmic horizon is not a distant mountain range you could one day cross. It is the ultimate boundary of information, a frontier defined by light itself. Think of the universe as a vast, dark ocean, and we are a single ship adrift. The light from distant shores, from other ships and lighthouses, takes time to travel across the water to reach our eyes. Some of that light has been journeying for nearly the entire age of the universe, for about 13.8 billion years. The farthest shores we can see are those whose first light is only just arriving here now. This creates a sphere around us, a bubble of visibility known as the observable universe. The edge of this bubble is our particle horizon. It is not that nothing exists beyond it. It is that the light from those outer realms has not had enough time to reach us yet. In fact, because space itself is stretching, that light may never reach us at all. The universe is simply too young and expanding too quickly for us to see its full extent. We are forever trapped inside a bubble of observation, a Hubble volume, limited by the finite speed of light and the relentless passage of time. Every star, every galaxy we will ever know, resides inside this sphere. Everything else, the true vastness of the cosmos, is hidden behind a curtain we cannot pull back. This fundamental limit is why the quiet expansion happens in the dark. It is a process playing out in the true cosmos, far beyond the edges of our tiny, illuminated stage. This fundamental limit of our cosmic horizon is not the only boundary we face. A deeper mystery is unfolding right here within the data we can collect. Our most precise measurements of the cosmos are now telling two different, conflicting stories about the very expansion of space. This is the Hubble tension, a crack appearing in the foundation of modern cosmology. The problem centers on the Hubble constant, which is simply the number that tells us how fast the universe is expanding today. For decades, we assumed this was a single, straightforward value. We have two primary ways to measure it. The first method looks back to the infant universe, to the afterglow of the Big Bang known as the cosmic microwave background. By studying the subtle patterns in this ancient light, we can calculate how fast the universe should be expanding now. The second method uses the local universe, observing the distances and speeds of nearby stars and the brilliant explosions of dying stars called supernova. These act as cosmic mile markers, allowing us to measure the expansion rate directly. The shocking result is that these two methods do not agree. The early universe method suggests a slower, more sedate expansion rate. The local universe method insists it is faster. The measurements are so precise that the gap between them is no longer a minor error. It is a significant and stubborn discrepancy. This is not a simple miscalculation. It is a direct conflict between our deepest observations of the cosmos. If our most trusted tools are giving us contradictory answers, it suggests that our standard model of the universe, a model that has been incredibly successful, might be missing a crucial piece. The Hubble tension could be the first tangible evidence that something is happening in the cosmos that our current physics cannot explain. It is a whisper from the darkness, a hint that the quiet expansion we cannot see might be governed by rules we have yet to discover. This discrepancy in our cosmic measurements points toward a hidden actor on the grandest stage, the prime mover of the quiet expansion. We call this mysterious force dark energy. It is not a substance you could touch, but a property of empty space itself, a latent energy woven into the fabric of the cosmos. Its discovery was one of the most shocking in modern science. In the late 1990s, two independent teams were observing distant stellar explosions, supernova, to measure how the universe's expansion has changed over time. Everyone expected to find that the pull of gravity was slowing the expansion down. Instead, they found the opposite. The expansion is speeding up. It is as if you tossed a ball into the air, and instead of falling back down, it shot away from you faster and faster. Something is overcoming the relentless pull of gravity, pushing galaxies apart with ever-increasing force. That something is dark energy. We now believe it constitutes about 68% of everything in the universe. We do not see it, but we see its effect everywhere, in the way galaxy clusters are being pulled apart on the largest scales. The leading idea is that dark energy is a cosmological constant, a steady, unchanging energy density inherent to the vacuum of space, an idea Einstein himself once proposed and then discarded. But is it truly constant? Another possibility is that dark energy is a dynamic field, which scientists call quintessence. This would be a force that could change in strength over time, perhaps growing stronger or weaker. This is a crucial question for the quiet expansion. If dark energy is not constant, its behavior in the vast, unobservable universe beyond our horizon could be profoundly different. It could be orchestrating a more rapid, more dramatic stretching of space in the eternal dark, a silent symphony we can only infer from the faintest of echoes. But the accelerating expansion driven by dark energy was not the universe's first era of incredible growth. Long before this quiet stretching began, the cosmos was forged in a firestorm of exponential growth known as inflation. For a fleeting sliver of time, far less than the blink of an eye, the universe did not just expand, it exploded in scale. This inflationary period was the primordial roar that set the stage for everything to come, a burst of unimaginable violence that made the subsequent 13.8 billion years of cosmic evolution seem almost peaceful by comparison. The theory of inflation solves several profound puzzles about our universe. Why does the cosmos look so uniform in every direction? How did the vast cosmic structures we see today, like galaxies and clusters, first begin to form? Inflation provides an elegant answer. It proposes that a tremendous field of energy, a sort of anti-gravity, caused space itself to stretch faster than the speed of light. This hyper-stretching took a tiny, tangled patch of the early universe and smoothed it out to an incredible degree, much like rapidly pulling on a crumpled sheet of paper until it lies perfectly flat. This explains the remarkable uniformity we see in the cosmic microwave background, the ancient afterglow of the Big Bang. That background radiation is almost exactly the same temperature in every part of the sky we observe, a fact that only makes sense if those distant regions were once in close contact before being flung apart by inflation. But this smoothing process was not perfect. On the smallest quantum scales, tiny fluctuations were inevitable. Inflation stretched these microscopic ripples into cosmic proportions, seeding the entire universe with faint overdensities, the gravitational seeds around which all galaxies and galaxy clusters would eventually gather. The quiet expansion we observe today, the steady work of dark energy, is the long-term legacy of that initial, violent burst. It is as if the universe began with a single, deafening thunderclap of inflation, and we now live in the lingering, gentle echo of that first sound, an echo that is still pushing the cosmos apart. This relentless stretching of the cosmos is driven by a profound mystery woven into the fabric of reality itself. The engine of the quiet expansion may be found in the very nature of space, and the startling answer to a simple question. Is the vacuum of space truly empty? Our intuition says yes, but the laws of quantum physics reveal a far more chaotic and vibrant picture. According to quantum field theory, what we perceive as a perfect void is actually a seething sea of activity. At the tiniest imaginable scales, pairs of virtual particles and their antiparticles are constantly flickering into existence and then annihilating each other almost instantly. This chaotic froth of spontaneous creation and destruction is known as quantum foam. It means that nowhere in the universe is ever truly still or empty. Every single cubic centimeter of space, from the void between galaxies to the air in front of you, is teeming with this brief, energetic dance. The energy associated with this perpetual motion is called vacuum energy or zero-point energy. It is the lowest possible energy that a quantum physical system can have, and it is never zero. This energy of empty space is the leading candidate for the source of dark energy. It is as if space itself possesses a latent, repulsive force, an inherent pressure that causes it to stretch. This idea connects back to Einstein's cosmological constant, a term he introduced into his equations to represent a stable energy density of the vacuum. But this elegant solution confronts a monumental problem, one of the greatest mismatches in all of science. When physicists calculate how much energy this quantum foam should be generating, based on our well-tested theories, the number they get is astronomically large. We are talking about a value with 120 zeros after it. This predicted energy should be so unimaginably powerful that it would have ripped the universe apart in its first moments, preventing stars, galaxies, or even atoms from ever forming. And yet, our observations of dark energy tell us its effect is incredibly small, a whisper of a push. This staggering mismatch between prediction and reality is the cosmological constant problem. It means our two most successful theories, quantum mechanics and general relativity, are giving us completely different answers about the most basic property of space. The quiet expansion we observe hints that the true nature of the vacuum is far stranger and more subtle than we ever conceived. The dark energy we measure might be only a faint remnant of that titanic quantum energy, or perhaps a sign that different, unknown rules govern the vacuum on the largest cosmic scales. The silent growth of the universe appears to be an intrinsic property of space itself, a fundamental whisper emanating from the restless nothingness that fills the cosmos. So if the vacuum of space itself holds this mysterious energy, what does that mean for the vast cosmos we can never see? Our cosmic horizon acts as an impenetrable curtain, but cosmology gives us a powerful tool to peer beyond it in theory, a guiding assumption known as the Cosmological Principle. It states that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means the overall distribution of matter and energy is smooth and even, like a perfectly risen loaf of raisin bread where each slice contains roughly the same number of raisins. Isotropic means it looks the same in every direction you look. There are no special places and no preferred center. This principle is the bedrock of modern cosmology, and it allows us to make a profound inference. The part of the universe beyond our horizon, the part forever hidden from our telescopes, is probably very much like our own local patch. It should be filled with similar galaxy clusters, similar cosmic voids, all governed by the same laws of physics and all subject to the same quiet expansion driven by dark energy. This leads to a staggering, almost humbling possibility. If the universe is truly infinite, then beyond our horizon lies an endless repetition of our own observable universe. There could be other Hubble volumes, other spheres of visibility, each containing an identical distribution of galaxies, stars, and perhaps even planets. The sheer scale of such a reality is difficult to grasp, but we must ask a critical question. Is the cosmological principle universally true, or is it merely a local phenomenon? What if our observable universe is just one neighborhood in a much grander and more varied cosmic metropolis? Some theories in quantum cosmology suggest that during that initial burst of inflation, different regions of space could have stopped inflating at different times, creating a vast mosaic of pocket universes, often called a multiverse. In this breathtaking scenario, the conditions beyond our horizon could be radically different. The strength of fundamental forces, the number of spatial dimensions, even the value of the cosmological constant that drives the quiet expansion could all be different in these other domains. Some of these patches might have laws of physics so alien that matter as we know it could never coalesce. Others might have experienced a far more violent dark energy, tearing themselves apart in an instant, while others might have collapsed back in on themselves long ago. Our entire cosmic history, from the Big Bang to the formation of our galaxy, might be just one possible outcome in an infinite tapestry of realities. The relentless quiet expansion we detect is then the faint, uniform signal from our own local pocket, a single note in a silent, unimaginably vast symphony of universes, most of which we are forever isolated from. This silent, relentless stretching of space dictates a final outcome for everything we see. The ultimate fate of our universe hinges entirely on the precise character of dark energy, the mysterious force driving the quiet expansion. While we cannot see its behavior in the distant dark, our local observations allow us to project three primary scenarios for the cosmic end. The first and currently most supported model is known as the heat death or the Big Freeze. In this future, dark energy remains a constant, gentle pressure. The expansion continues forever, growing ever faster. Galaxies beyond our local group will first fade from view, their light stretched beyond detection. Then, star formation will cease as the raw material for new stars is used up. Existing stars will burn out one by one, leaving behind cold, dead remnants like black holes, neutron stars, and frigid white dwarfs. Over incomprehensible eons, even these remnants will decay. The universe will approach a state of absolute equilibrium, a perfectly uniform, frigid void where the temperature everywhere drops to just a fraction of a degree above absolute zero. No energy gradients will remain, no heat can flow, and all organized motion becomes impossible. It is a quiet, gradual fading of all light and life into a permanent, static darkness. A second, more dramatic possibility is the Big Rip. This scenario unfolds if dark energy is not constant, but instead grows stronger over time. Imagine the repulsive force of the vacuum increasing, becoming more powerful than any of the fundamental forces that hold reality together. First, the expansion would tear apart the gravitational bonds holding galaxy clusters together. Then, individual galaxies would be shredded. As the force intensifies, it would overcome the gravity holding stars within those galaxies. Later, it would rip apart solar systems. In the final, terrifying moments, the strengthening dark energy would overwhelm the electromagnetic forces holding planets and stars together, then the nuclear forces binding atoms. In a final instant, every single atom, every proton and neutron would be torn asunder. The fabric of spacetime itself would be ripped to pieces. The universe would end not with a whimper, but with a violent, fundamental dissolution of matter and space. The third classic model offers a cyclical alternative, the Big Crunch. This would require that the density of matter in the universe is high enough, or that dark energy weakens and reverses, so that the expansion eventually slows, halts, and turns inward. Gravity would begin pulling everything back together. Galaxies would start to merge as they fall toward each other. The background temperature of the universe, currently just a few degrees above absolute zero, would begin to rise. As everything compresses, the sky would glow hotter and hotter, first with infrared, then with visible light. The universe would head toward a fiery, ultra-dense state, a mirror of the Big Bang, potentially collapsing into a singularity. Some theories even suggest this singularity could trigger a new Big Bang, giving birth to a new universe in an endless cycle of expansion and contraction, a cosmic phoenix. So which of these fates is most likely? Current observations of the quiet expansion in our local universe, measuring the behavior of dark energy through supernova and other probes, most strongly support the first model, the heat death. The data so far suggests dark energy is consistent with a cosmological constant, a steady, unchanging force. This points toward the long, cold fade, yet the uncertainty is profound. The evidence for a perfectly constant dark energy is not yet absolute. The faintest hint that its strength might be changing could shift the entire cosmic forecast from a slow freeze to a violent tear. The quiet expansion we witness today is more than a curiosity. It is the opening chapter of the universe's final story, a tale whose ending is being written in the dark just beyond our sight. While dark energy works to push the cosmos apart, another unseen force is responsible for holding it all together, building the very architecture of the universe. This is the role of dark matter, the invisible cosmic scaffolding that provides the gravitational backbone for everything we see. Think of dark matter as a vast, unseen framework, like the steel girders inside a massive skyscraper. We cannot see the girders from the outside, but without them, the entire structure would collapse. In the same way, dark matter, which makes up about 27% of the cosmos, does not emit, absorb, or reflect any light. It is completely transparent, yet its gravitational pull is the dominant force shaping the largest structures in existence. The first compelling evidence for this mysterious substance came from the way galaxies spin. When astronomers measured the rotation speeds of stars within spiral galaxies, they found something astonishing. According to the laws of gravity, stars on the outer edges of a galaxy, far from the bright center, should be moving much more slowly than those near the core, just as the outer planets in our solar system orbit the Sun more slowly than the inner ones. But the data revealed the opposite. Stars at the galactic outskirts were whipping around just as fast as those near the center. The only way this makes sense is if the entire galaxy is embedded within a massive, invisible sphere of matter, a dark matter halo whose gravity is pulling on those distant stars, accelerating their motion. Without this halo's immense gravitational grip, the galaxy would simply fly apart. We see further proof through a phenomenon called gravitational lensing. The immense gravity of a massive object like a galaxy cluster can warp the fabric of spacetime around it, acting like a lens that bends and distorts the light from more distant galaxies behind it. By studying the degree of this distortion, astronomers can map the cluster's total mass. Time and again, these maps show that the visible galaxies and hot gas account for only a small fraction of the mass required to create such a powerful lens. The majority of the gravity, and therefore the mass, is coming from an invisible source, dark matter. This cosmic scaffold dictates where galaxies form and how they cluster together in a vast cosmic web. The ongoing quest to identify what dark matter actually is represents one of the greatest challenges in physics. The leading candidate is a hypothetical class of particles known as WIMP, or weakly interacting massive particles. These particles would barely interact with normal matter, passing through our planet and our bodies by the billions every second without a trace. Experiments deep underground are trying to catch the incredibly rare flash of energy when one of these particles might collide with an atomic nucleus. Other scientists are searching for different candidates like actions, which are incredibly light particles, but the implications stretch far beyond our local universe. Just as dark matter's gravity sculpts the galaxies within our observable bubble, its distribution in the vast, unobservable cosmos beyond our horizon must be shaping the grandest dynamics of the quiet expansion. The gravitational pull from these unseen dark matter structures in the eternal dark could be subtly tugging on our entire local group of galaxies, influencing the very rate at which we perceive space to be stretching. The silent expansion is not just a solo performance by dark energy, but a complex duet with the invisible architect of cosmic structure, a partnership whose full nature remains hidden in the dark. This ancient glow is the closest we can get to witnessing the birth of the cosmos. The cosmic microwave background radiation is a fossil of light, a snapshot from a time when the universe was a mere 380,000 years old. Before this moment, the universe was a hot, dense fog of plasma, where light was constantly scattered by free electrons, making it opaque. As the cosmos expanded and cooled, electrons and protons finally combined to form the first neutral atoms. In that instant, the fog cleared. Light, for the first time, could travel freely across space. That first flash of liberated light is what we detect today as the CMB, stretched and cooled by 13.8 billion years of expansion into a faint microwave whisper that uniformly bathes the entire sky. It is the ultimate wall of our observable universe, the final screen beyond which we cannot see. Satellites like Planck have mapped this afterglow with breathtaking precision, revealing that it is not perfectly uniform. It is imprinted with tiny temperature fluctuations, variations of just a few millionths of a degree. These minute ripples are not random noise. They are a cosmic code, a detailed blueprint that encodes the universe's fundamental properties. The patterns in this light tell us the precise proportions of ordinary matter, and dark energy. They confirm the geometry of the cosmos is flat, meaning parallel lines will never meet on the largest scales. And most critically for our story, they provide our cleanest measurement of the universe's early expansion rate, a value that now clashes with our local measurements, creating the Hubble tension. The CMB acts as a cosmic backlight, illuminating not just the infant universe, but also the limits of our current understanding. Those faint temperature spots are the amplified quantum seeds from the inflationary epoch, the initial conditions that set everything in motion. They are the reason galaxies and vast cosmic voids eventually formed, and they are the primary evidence that the quiet expansion we witness today was orchestrated by forces in the universe's first moments, a destiny written into the fabric of reality from the very beginning. The theory of inflation does not end with the smooth, uniform cosmos we observe. It hints at a reality of staggering proportions, a multiverse. Our entire cosmic history, from the first stars to the quiet expansion we measure, may be just one story unfolding in a single bubble within an infinite, frothing meta-universe. This is not a single idea, but a spectrum of possibilities emerging from our most fundamental theories of physics. One version comes from the quantum many-worlds interpretation. It suggests that every time a quantum particle faces a choice, the entire universe splits, creating a new branch for every possible outcome. In this view, a near-infinite number of parallel realities are constantly budding off, each one real and complete, but forever separate from our own. A different, even more vast conception arises from string theory in what is known as the landscape. This theory proposes an astronomical number of possible stable configurations for the extra dimensions it requires, perhaps 10 to the 500 different versions. Each configuration corresponds to a universe with a unique set of physical laws and constants. Eternal inflation provides the engine to populate this landscape. In this model, the inflationary energy field does not switch off everywhere at once. Instead, it decays in localized patches, like bubbles forming in a boiling pot of water. Each of these bubbles is a new universe with its own Big Bang and its own subsequent evolution. Our universe is one such bubble. The quiet expansion we witness is simply the local behavior of our bubble's own vacuum energy. But in the greater meta-universe beyond our horizon, other bubbles are constantly forming, each with its own physics. Some might have a stronger nuclear force, making stars burn out in millions of years. Others might have a weaker gravity, preventing planets from ever forming. Some might have a cosmological constant so immense they ripped apart instantly, while others might have collapsed back into nothingness. The profound question is whether this radical idea can ever be tested. If these other universes are permanently beyond our causal contact, separated by inflating space that moves faster than light, does the multiverse remain a philosophical speculation rather than a scientific theory? Scientists are searching for subtle clues. Perhaps our bubble universe collided with another in the distant past, leaving a faint imprint in the cosmic microwave background, a kind of cosmic bruise. Or perhaps the specific, seemingly fine-tuned values of our physical constants, which allow for our existence, only make sense if we are one among many. The multiverse hypothesis reframes our place in existence. It suggests that the quiet expansion and the specific laws we study are not the universal rule, but merely our local bylaw, a single paragraph in an infinite library of physical realities. Studying a cosmos we cannot directly see requires a kind of scientific detective work, piecing together the story from subtle, indirect clues. Our most powerful tools for mapping the quiet expansion rely on finding consistent patterns and reliable mileposts scattered across the sky. One of these key patterns is known as Baryon acoustic oscillations. To understand this, think back to the early universe when it was a hot, dense soup of particles and light. Pressure waves, much like sound waves, rippled through this primordial plasma. When the universe cooled enough for atoms to form, freeing the light we now see as the cosmic microwave background, these waves froze in place, imprinting a specific scale on the distribution of matter. This scale acts as a cosmic ruler, a standard length etched into the fabric of the universe. By measuring the apparent size of this ruler at different distances, which means looking back in time, astronomers can gauge how much the universe has stretched over billions of years. It provides a direct measurement of the expansion history, a fundamental check on the work of dark energy. Another crucial tool involves finding what astronomers call standard candles. These are astronomical objects with a known intrinsic brightness. The most famous of these are Type Ia supernova, the spectacular explosions of white dwarf stars. Because we understand the physics behind these explosions, we know how bright they truly are at their peak. By comparing this known intrinsic brightness to how dim they appear from Earth, we can calculate their distance with remarkable precision. It is like knowing the exact wattage of a light bulb. By seeing how faint it looks, you can tell how far away it is. In the late 1990s, it was the observation of these very supernova that revealed the expansion was not slowing down but accelerating, leading directly to the discovery of dark energy. These cosmic beacons allow us to chart distances across vast cosmic voids, providing the direct evidence for the quiet expansion we measure today. A third method peers at the universe through a warped lens, quite literally. Weak gravitational lensing surveys map the cosmos by observing how the gravity of unseen matter, primarily dark matter, distorts the light from billions of background galaxies. This is not the dramatic lensing that creates giant arcs, but a far more subtle shearing effect, a slight stretching of the shapes of distant galaxies. By statistically analyzing the patterns of this distortion across huge swaths of the sky, we can create a mass map of the invisible cosmic scaffolding. This tells us how the large-scale structure of the universe, built by dark matter, has evolved over time, since the growth of this structure is directly opposed by the stretching force of dark energy. These lensing maps provide a vital, independent measure of its strength and constancy. Each of these techniques, the frozen sound waves, the brilliant stellar explosions, and the warped light, carries its own set of uncertainties and potential for systematic error. Calibrating distances across billions of light-years is fraught with challenges, from interstellar dust dimming the light to the inherent difficulty of perfectly understanding the physics of our standard candles. The Hubble tension itself may be a symptom of these hidden errors, a signal that our most trusted cosmic rulers might need a more precise calibration. Pushing past these limitations is the daily work of cosmology, a relentless effort to read the faintest writing in the dark, striving to understand a universe that forever retreats from our view. The cosmic landscape is not a uniform sea of galaxies, but a vast, intricate web. On the grandest scales, the universe is structured like a colossal sponge, with dense clusters and long, winding filaments of galaxies surrounding enormous, nearly empty bubbles known as cosmic voids. These voids are not small pockets of nothingness. They are the dominant feature of the cosmos, immense regions of space that can span hundreds of millions of light-years and contain very few, if any, galaxies. Within these caverns of near-nothingness, the rules of expansion are subtly different. The quiet expansion is not perfectly uniform everywhere. Because a void has such a low density of matter, the gravitational pull from within it is exceptionally weak. There is very little gravity holding that region together or slowing its growth. This allows the inherent push of dark energy, combined with the pull from the dense matter in the surrounding walls and filaments, to stretch the void itself faster than the cosmic average. It is as if you had a rubber sheet with heavy weights clustered in some areas. The empty spaces between the weights would stretch more easily and rapidly. These voids are not static holes, they are actively growing, their emptiness becoming more profound with time. This makes them perfect natural laboratories for studying the pure effects of dark energy, far from the complicating gravitational tug of war found in crowded galaxy clusters. By meticulously mapping the shapes, sizes, and growth rates of these voids, astronomers can take the temperature of the quiet expansion in its most extreme environment. They can ask a critical question: does dark energy behave exactly the same way in the profound emptiness of a void as it does within our more typical galactic neighborhood? The slightest deviation could reveal that dark energy is not a simple constant after all, but something more dynamic. The silent growth of these vast, dark regions may hold the key to understanding the ultimate fate of everything, written not in the light of stars, but in the relentless stretching of the void itself. This remarkable fine-tuning of the cosmos presents a profound puzzle. The strength of dark energy, the very force behind the quiet expansion, appears to be perfectly calibrated for our existence. If its value were just a little bit larger, the repulsive force would have been so powerful in the early universe that it would have ripped apart the delicate gravitational seeds before they could ever form galaxies, stars, or planets. There would be no cosmic structures, only a thin, expanding haze of particles, Conversely, if dark energy were slightly weaker, its push might not have been enough to counterbalance gravity's pull over the long term. The universe could have slowed its expansion much sooner and collapsed back in on itself in a big crunch, ending long before complex life had a chance to emerge. The value we measure is not just convenient, it seems necessary for observers like us to be here. This leads to a controversial but fascinating line of reasoning known as the Anthropic Principle. In its simplest form, it suggests that the universe must be compatible with the conscious life that observes it. We should not be surprised to find the constants of nature set to values that allow for our existence, because in a universe where they were not, there would be no one to be surprised. This is not an explanation of why the constants have these values, but rather a recognition of a profound selection effect. We can only measure a universe that has the right conditions for us to live in. The quiet expansion has the specific, gentle strength it does because we are here to witness it. This idea sparks intense debate. For some scientists, it feels like a philosophical retreat, a way of avoiding a deeper physical explanation. For others, it is a necessary piece of the puzzle, especially when considered alongside the multiverse. If a vast multiverse exists with countless pocket universes, each with randomly different physical constants and different strengths of dark energy, then it becomes statistically inevitable that a few of those universes will, by pure chance, have the perfect conditions for life. We find ourselves in one of those rare, hospitable bubbles simply because we could not exist anywhere else. Our entire cosmic history, from the first stars to the quiet expansion, is not the product of a single, designed universe, but the outcome of a cosmic lottery we were destined to win. This perspective dramatically reframes our place in the cosmos. It suggests that the universe is not necessarily fine-tuned for life, but that life is a rare and precious adaptation to a cosmos that is, for the most part, vast, empty, and hostile. The quiet expansion we measure is not a universal rule, but our local reality, one silent note in a chaotic symphony of possibilities. This fundamental divide in our understanding of reality runs deeper than the dark energy it tries to explain. Our two most powerful descriptions of the cosmos, general relativity and quantum mechanics, speak completely different languages. General relativity paints a beautiful, continuous picture of space and time as a smooth, flexible fabric, warped by mass and energy. It perfectly describes the dance of planets and the bending of light around galaxies. Yet, at the smallest scales, the quantum world is a realm of frenetic jumps and probabilities, where particles flicker in and out of existence and nothing is truly smooth or certain. These two theories are brilliant in their own domains, but they cannot both be correct at the same point. They fundamentally disagree on the nature of reality itself. This conflict becomes critical in the most extreme environments imaginable, like the heart of a black hole or the very first moment of the Big Bang, where immense gravity meets the quantum realm. To truly understand the engine of the quiet expansion and to know what dark energy truly is, we must find a theory that unifies them, a theory of quantum gravity. This is the single greatest unsolved problem in all of physics. The quest is to find a single set of rules that describes how gravity works when space and time themselves become grainy and uncertain. Two leading candidates offer radically different visions of this unified reality. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating loops of energy. Each distinct vibration pattern corresponds to a different particle, like an electron or a quark, and one specific vibration is thought to be the carrier of the gravitational force, the graviton. To make the math of these vibrating strings work, the theory requires more than the three spatial dimensions we experience. It suggests there could be 6 or 7 extra spatial dimensions, curled up into shapes so small we never notice them. In this framework, the properties of our universe, including the strength of dark energy, could be determined by the specific geometry of these hidden dimensions. The quiet expansion might be a direct consequence of how our particular slice of reality is folded within a higher dimensional space. The other major approach, loop quantum gravity, takes a different path. It does not propose extra dimensions. Instead, it suggests that space itself is not smooth and continuous, but is woven from a fabric of tiny, finite loops. Imagine the fabric of spacetime as a weave, with the individual threads representing the smallest possible units of area and volume. This fabric is granular or pixelated at the tiniest scale imaginable, the Planck length. In this theory, the Big Bang was not a singular point of infinite density, but a moment where this fabric of loops was rebounding from a previous phase of the universe, a big bounce. This has a profound implication for the quiet expansion. If space is composed of a finite number of these quantum threads, then the energy of the vacuum, which we call dark energy, could be a natural property of this woven structure. Its strength would be determined by the fundamental graininess of space. The expansion we see could be the result of this quantum fabric relaxing or evolving over cosmic time. The ultimate theory of quantum gravity, whether it is one of these or something entirely new, would allow us to peer into the heart of the cosmic voids. In those vast, empty regions where the quiet expansion reigns supreme, far from the clutter of galaxies, the true quantum nature of spacetime might be most visible. It is here that we might finally see if the vacuum energy is truly constant, or if it flickers and evolves, driven by the fundamental grain of reality itself. Unifying gravity with the quantum world would not just complete our picture of physics, it would finally illuminate the deepest driver of the cosmic story, revealing the true source of the silent push that is shaping the destiny of everything. Yet even the cosmic microwave background, our most pristine snapshot of the infant cosmos, holds a strange and unsettling secret. As scientists meticulously charted the faint temperature ripples across the sky, they noticed a pattern that defied simple explanation, a large-scale alignment so peculiar it earned the dramatic nickname, the axis of evil. This is not a malevolent force, but a mysterious statistical anomaly in the data. The tiny hot and cold spots in the ancient light are not scattered randomly as the standard cosmological model predicts. Instead, they show unexpected correlations, a subtle alignment that curiously seems to orient itself with the plane of our own solar system. The immediate and most conservative explanation is that this is simply a fluke, a statistical ghost in the machine that will vanish with more precise measurements. Another possibility is that it stems from an unaccounted-for systematic error, perhaps a subtle effect from how we subtract the foreground glow of our own galaxy. But the alignment has stubbornly persisted, challenging one of cosmology's most cherished beliefs. The cosmological principle states that the universe should have no preferred direction, no center, and no special axis. The axis of evil anomaly whispers that on the very largest scales, this fundamental assumption might not be entirely true. Could this be a genuine crack in our model, a clue about the true nature of the cosmos beyond our observable horizon? One tantalizing idea is that this alignment is a relic from the era before inflation began, a fossil imprint of a more structured, pre-existing universe. Perhaps the rapid stretching of inflation did not completely erase this primordial structure, leaving behind a faint directional memory etched into the first light. Alternatively, this axis could be a sign of something else entirely, a vast, unseen influence tugging at the entire fabric of our local universe. the gravitational pull from an immense, over-dense region lurking in the unobservable darkness beyond our particle horizon could theoretically create such a large-scale alignment, warping the very space through which the CMB light travels to reach us. If true, this would mean the quiet expansion we measure is not happening in a perfectly uniform void, but is being subtly shaped by gravitational tides from the true, hidden cosmos. The axis of evil remains an open case, a cosmic detective story written in the oldest light we can see, challenging us to question whether our entire observable universe is just a tilted room in an infinite and far more complex mansion. These cosmic mysteries demand a new generation of eyes on the sky. A silent revolution is underway in observational cosmology, driven by telescopes of such power they will peer deeper into the dark than ever before. These are not merely larger versions of past instruments, but entirely new tools designed to dissect the quiet expansion with surgical precision. They will map the cosmos in 3 dimensions, tracing the invisible scaffolding of dark matter and measuring the subtle tug of war between gravity and dark energy across billions of years. The James Webb Space Telescope, already gazing into the infrared depths, is our time machine to the era of the first galaxies. By seeing these ancient structures form, we understand the initial conditions that the quiet expansion would later work upon. But Webb is just the beginning. The Nancy Grace Roman Space Telescope, set to launch later this decade, will conduct a survey of staggering breadth. Imagine a panoramic movie of the cosmos, one that will capture the positions and shapes of billions of galaxies across vast stretches of space and time. This immense catalog will allow scientists to measure the growth of cosmic structures and the rate of expansion with a level of accuracy that could finally resolve the Hubble tension. It will see the clearest picture yet of how dark energy has shaped the universe. On a mountaintop in Chile, the Vera C, Rubin Observatory's massive camera will scan the entire southern sky every few nights, creating an unprecedented dynamic map of the cosmos. It will detect billions of new galaxies and millions of supernovae, each exploding star a fleeting standard candle that helps calibrate our cosmic distance ladder. This relentless nightly watch will track the most minute changes in the sky, revealing the subtle effects of the quiet expansion in real time. Meanwhile, the Euclid spacecraft, already on its mission, is specifically designed to create the most extensive and accurate map of the dark universe. By observing the weak gravitational lensing of distant galaxies, Euclid will trace the distribution of dark matter with exquisite detail, showing us how the cosmic web has been stretched and pulled by the relentless push of dark energy. Together, these observatories form a coordinated assault on the unknown. They will measure the universe's expansion history not as a single number, but as a detailed story, charting every chapter from the primordial dawn to the present day. They will stare into the cosmic voids, those vast, empty laboratories, to see if the quiet expansion proceeds exactly as our models predict. Could their data reveal that dark energy is not constant but is evolving? Might they detect entirely new phenomena, forces or fields we have not yet even named, operating in the profound darkness beyond our current sight? The answers are written in the light of billions of distant suns, light that is only now arriving at our doorstep, carrying secrets from the deep dark. This unsettling possibility forces us to confront a deeper question. What is nothing? We tend to think of a vacuum as a perfect, empty void, a true and final nothingness. Yet, as we have seen, the quantum universe laughs at this idea. The vacuum of space is not empty. It is a vibrant sea of quantum potential, filled with the fleeting energy of virtual particles. This leads to a startling and profound hypothesis. What if our vacuum, with its specific energy and laws, is not the most stable state possible? What if it is merely a false vacuum, a temporary resting place in a much grander energy landscape? The theory of vacuum decay suggests exactly that. It proposes that our entire universe, with its particular strength of forces and its gentle dark energy, could be metastable. It is like a ball resting in a small dip on the side of a vast valley. The ball seems stable, but it is not at the absolute lowest point. A nudge, a random quantum fluctuation, could send it rolling down into the true valley floor. In cosmic terms, this nudge would create a bubble of true vacuum. This bubble would not be made of matter, but of a new, fundamental state of space itself, with completely different physical laws. The walls of this bubble would expand in all directions at nearly the speed of light. From the outside, you would see nothing but a shimmering sphere of energy. But inside, the very rules of reality would be rewritten. The strength of the forces that hold atoms together could vanish. The concept of matter as we know it would cease to exist. The quiet expansion we measure would be instantly and catastrophically overthrown, replaced by a new, unknown rate of expansion dictated by this new, lower energy vacuum. The stability of our entire reality hinges on the behavior of one particular field, the Higgs field. This is the field that gives elementary particles their mass, and its current value is what makes our universe what it is. Our best calculations suggest this field is likely in a metastable state. It is not perfectly stable, but it is stable enough to have lasted for 13.8 billion years. The probability of such a decay event starting in any given place is astronomically low, but the universe is unimaginably vast and old. In the endless expanse beyond our cosmic horizon, across trillions of light years we can never see, the dice are being rolled constantly. It is statistically possible, perhaps even inevitable, that somewhere in that eternal dark, a bubble of true vacuum has already formed and is now expanding, silently rewriting the cosmos in its wake. This means the quiet expansion we observe could be a temporary local condition, a calm before a storm that we will never see coming. The silent growth of space might one day be interrupted not by a slow freeze or a violent rip, but by an instantaneous and fundamental erasure of the laws of physics, a final and silent end to the universe as we understand it. This radical notion questions the very nature of our three-dimensional reality. The holographic principle proposes that our universe, with all its stars, galaxies, and the space between them, might be a projection from a two-dimensional surface at its outer boundary. All the information that makes up you, me, and every galaxy within our cosmic horizon could be encoded like the pixels on a vast spherical screen, a screen we can never actually see. This idea did not come from pure speculation, but from a deep puzzle about black holes. When matter falls into a black hole, it seems to vanish, taking its information with it. This violates a core tenet of quantum physics, which states that information can never be truly destroyed. The resolution proposed by physicist Gerard T. Hooft and expanded by Leonard Susskind was breathtaking. They suggested that all the information about what falls into a black hole is not lost inside, but is instead perfectly preserved on its event horizon, the point of no return. The black hole's surface area, not its volume, holds the data. This is like a cosmic thumb drive where information is stored on the shell, not within the drive itself. Now take this concept and apply it to the biggest system we know, our entire observable universe. Our cosmic horizon, the ultimate limit of what we can see, acts like a giant event horizon. The holographic principle dares to suggest that everything within this sphere, every particle interaction, every galaxy spinning in the void, and even the quiet expansion we measure, is a holographic projection from the data encoded on this distant two-dimensional surface. We are not living inside a universe, but rather within an image being displayed on its outermost shell. This immediately challenges our most basic assumptions about locality, the idea that objects can only be influenced by their immediate surroundings. In a holographic universe, what happens here could be directly linked to information processed on the boundary, billions of light-years away. The quiet expansion, the relentless stretching of space driven by dark energy, might not be a local phenomenon at all. It could be a consequence of how the information on the cosmic horizon is being processed and updated. The dynamics of the entire cosmos could be written in a code we are only beginning to decipher, a code that operates on a surface forever beyond our reach. If this is true, then the true engine of reality is not in the volume we inhabit, but on a distant, flat screen, making our rich three-dimensional experience a magnificent and convincing illusion. But the cosmic web is not shaped by gravity alone. Another force, one we know from everyday life, weaves its way through the vast emptiness between the galaxies. Magnetic fields, once thought to be confined to stars and planets, are now understood to permeate the colossal voids themselves. These are not the neatly ordered fields of a simple bar magnet, but a chaotic tapestry of magnetic filaments stretching for millions of light-years. Their presence in such profoundly empty space is a profound mystery. Where did they come from? The leading theory points to the universe's tumultuous infancy. In the first moments after the Big Bang, tiny seed fields could have been generated by the violent churning of plasma, perhaps during the inflationary epoch itself. These weak, primordial fields would then have been stretched and amplified over billions of years by the motion of ionized gas, as galaxies formed and cosmic structures evolved. It is a ghostly fossil, a relic force from the dawn of time that has been woven into the expanding fabric of the cosmos. So what influence do these faint fields hold in the near-perfect vacuum of a void? While their strength is minuscule, a million times weaker than Earth's magnetic field, they are not insignificant. They can guide the sparse, superheated gas that drifts through these emptiness, influencing how it flows and perhaps even preventing it from collapsing to form new, dwarf galaxies. This subtle guidance acts as a background pressure, a faint resistance against the gravitational pull of dark matter. In the grand tug of war between the inward pull of gravity and the outward push of dark energy, these cosmic magnetic fields introduce a third, delicate player. They do not drive the quiet expansion, but they can subtly modify its local effects, shaping how matter is distributed within the growing voids. This reveals that the cosmic dark is not a simple, featureless emptiness. It is a dynamic medium filled with the faint whispers of ancient forces, a complex physics playing out in the quietest places imaginable. The same paradox that haunts black holes also applies to the edge of our entire reality. When Stephen Hawking first proposed that black holes could slowly evaporate, he presented a terrifying conclusion. The information about every star, planet, or book that fell into a black hole would be permanently lost, scrambled into a form of random thermal radiation. This information paradox struck at the heart of physics, suggesting that the universe could fundamentally forget its own past. Yet, this dilemma is not confined to the monstrous gravity wells in distant space. Our universe has its own horizon, the cosmological horizon, defined by the ultimate speed limit of light and the relentless quiet expansion. Everything beyond that horizon is receding from us faster than light can travel, meaning any information from those regions is forever lost to us. The question then becomes, is the cosmos itself, through its silent, accelerating growth, performing a similar act of cosmic forgetting? Is the history of galaxies now vanishing beyond our horizon being erased from our observable universe, just as information seems lost behind a black hole's event horizon. The work of physicists like Leonard Susskind suggests a profound connection. He and others fought Hawking's original idea, arguing that information must be preserved even if it is encoded on a black hole's surface. This led to the holographic principle, the radical idea that our three-dimensional reality might be a projection from a two-dimensional boundary. Apply this to our cosmic horizon, and the implications are staggering. The entire story of our observable universe, every particle and force, could be encoded on the spherical surface of our particle horizon. The quiet expansion, then, is not just stretching space, it is actively enlarging that cosmic hard drive, adding new pixels to the screen as more of the universe falls away beyond the light speed limit. This perspective suggests that the universe has thermodynamic properties, much like a black hole, with a defined temperature and entropy linked to its horizon. The relentless expansion increases this cosmic entropy, a measure of disorder. In a very real sense, the quiet expansion is increasing the overall disorder of the cosmos, not by destroying information, but by moving it permanently out of reach. The light and the history of countless galaxies have already crossed our horizon and are now receding into a silence from which they can never return. We are not losing the information in a fiery crash, but in a slow, gentle fade as the universe grows dark and quiet around us. This cosmic forgetting may be the ultimate fate of all we see, a gradual loss written not in violence, but in the serene, unstoppable stretching of the void. Our own galaxy is caught in a silent river flowing through the cosmos. The Milky Way is not drifting aimlessly in the expansion, but is being pulled, along with thousands of other galaxies, toward a specific point in the darkness. This vast, coherent motion is known as a bulk flow, a river of galaxies on an unimaginable scale, all moving in the same direction against the backdrop of the quiet expansion. The destination of this cosmic current is a mysterious region we call the Great Attractor. Its name evokes a powerful and hidden force, a gravitational anomaly so immense that it can tug on our entire local supercluster of galaxies. Think of the Hubble expansion as a steadily rising tide, lifting all boats. A bulk flow is like a powerful, localized current within that tide, pulling a specific flotilla of boats toward a single, unseen drain. For decades, the nature of this attractor was obscured because it lies in the zone of avoidance, a direction in space hidden behind the dense stars and dust of our own Milky Way's central plane. We were trying to map a hidden valley from behind a mountain range. What could possibly possess enough mass to cause such a large-scale deviation? The initial suspicion fell upon a known, massive concentration of galaxies known as the Norma cluster, which sits near the suspected center of this gravitational pull. This cluster is part of a larger structure, the Laniakea supercluster, a vast filament of galaxies that forms our cosmic continent, and of which the Great Attractor is a central gravitational anchor. But even the combined mass of Laniakea may not fully account for the strength of the flow. This leads to a deeper question. Does the existence of such a powerful and coherent bulk flow challenge the cosmological principle, the idea that the universe is uniform on the largest scales? The principle does not forbid structures and motions, but it assumes that these should average out over sufficiently vast distances. The scale of these flows is so immense that it tests the very definition of what constitutes a large enough scale. It suggests that our cosmic neighborhood for billions of light-years around might still be shaped by gravitational imbalances, by titanic concentrations of dark matter whose full extent we are still mapping. This makes the study of bulk flows absolutely critical. They are not just a curiosity, they are a diagnostic tool. By carefully measuring the precise speed and direction of these galaxy rivers, we can peer into the dark. We can map the total distribution of mass, both seen and unseen, in the cosmos around us. Each galaxy in the flow is like a leaf on a stream, its motion betraying the contours of the hidden gravitational landscape beneath the surface. This allows us to distinguish the local tug of a supercluster from the global, background push of dark energy. The quiet expansion is the overall theme of the cosmic story, but these bulk flows are the dramatic local subplots, driven by the gravitational pull of the universe's hidden architecture. They remind us that while dark energy stretches the fabric of space, the silent hand of dark matter is still sculpting its contours, pulling entire galaxies toward secrets we have only begun to uncover. Yet the violent burst of inflation is not the only possible origin for our cosmos. A radically different idea, known as the Ekpyrotic model, paints a picture of cosmic rebirth born not from a single explosion, but from a collision in a higher dimensional reality. In this framework, our entire three-dimensional universe is a membrane or brain, floating within a larger, hidden space called the bulk. The Big Bang, in this view, was not the beginning of time and space, but a dramatic event that occurred when our brain collided with another parallel brain. This collision converted the energy of impact into the hot, dense fireball we recognize as the start of our cosmic cycle. The name Ekpyrotic comes from the ancient Greek word for conflagration, evoking this idea of a world forged in a fiery clash. This model provides its own elegant explanation for the smoothness and structure of the universe. Before the collision, the two brains could have been drawn together over an immense period, their surfaces becoming flat, smooth, and parallel. This long, slow smoothing process, replacing the frantic hyper-stretching of inflation, would have ironed out any wrinkles, resulting in the uniform cosmos we observe. The quantum vibrations during this drawing together phase would have created the seeds for galaxies, just as in the inflationary model, but through a completely different physical process. This leads to a breathtaking possibility, the cyclic universe. In this extended vision, the quiet expansion we are now measuring is not a one-way journey toward cold emptiness. It is merely one phase in an endless cosmic loop. The universe expands, driven by dark energy, until matter and energy are spread so thin that their gravitational pull becomes negligible. Then the mysterious force of dark energy could transform, acting as a bridge to a new phase of contraction. The universe would slowly reverse its course, not in a chaotic crunch, but in a gentle, controlled gathering. Galaxies would draw nearer, space would condense, and the temperature would rise, all leading to another collision between the brains. This collision ignites a new Big Bang, and a new cycle begins. We could be living in just one iteration of an eternal sequence, with no true beginning and no final end. The quiet expansion is therefore not a countdown to oblivion, but a slow, rhythmic breath in an infinite cosmic life. This vision challenges the very meaning of an ultimate fate, suggesting our universe's story is not a linear narrative, but a verse in an endless poem, repeated across eternity. This relentless stretching of the cosmos is quietly rewiring the clock of the universe. Time itself is not a separate spectator to the quiet expansion. It is a fundamental player in the drama. The direction we call the arrow of time, the reason we remember the past but not the future, is deeply entangled with the growth of space. This connection is governed by a powerful concept known as entropy, which is essentially a measure of disorder in a system. The second law of thermodynamics states that the total entropy of the universe always increases, it never decreases. This is why a shattered glass does not spontaneously reassemble, and why heat flows from a hot object to a cold one, never the reverse. The quiet expansion provides the ultimate stage for this irreversible process. As space stretches, it creates more room for particles to spread out and for energy to disperse. Every new cubic light-year of void is a new canvas for disorder, a new opportunity for entropy to increase. The expansion is not just making the universe bigger, it is actively making it more disordered. This leads to a profound question about the ultimate end of time. In the distant future of a heat death, when the universe has reached maximum entropy and achieved a state of perfect frigid equilibrium, what happens to time? If there are no more energy differences to drive any process, no stars burning, no planets turning, no thoughts forming, then the very concept of before and after may lose its meaning. In a universe where nothing ever changes, can time be said to flow at all? The relentless march of the quiet expansion, by driving the increase of cosmic entropy, is what gives time its irreversible direction. It is the ultimate reason tomorrow is different from yesterday. This intimate link between the stretching of space and the flow of time points toward a deeper unity in the laws of physics, suggesting that the true nature of time is not a background constant, but a dynamic property that emerges from the cosmos itself. The faint whispers of the quantum foam are not the only echoes from creation. The violent expansion of inflation should have sent powerful tremors through the very fabric of space-time, generating primordial gravitational waves. These are not waves of light or sound, but ripples in the geometry of the cosmos itself, stretching and squeezing space as they travel. Detecting these ancient ripples would be the ultimate confirmation of inflation, a direct signal from the universe's first and most dramatic moment of growth. But how can we possibly detect a tremor that has been fading for nearly 14 billion years? The answer lies in a subtle pattern etched into the oldest light we can see. As these primordial gravitational waves washed through the hot plasma of the infant universe, they left a distinct signature on the cosmic microwave background. They imprinted a specific type of order on the light's orientation, a curling pattern known as B-mode polarization. Finding this pattern is like discovering the fossilized footprint of a cosmic giant. It is the primary goal of ambitious experiments like the BICEP array, located at the South Pole where the cold, dry air offers a crystal-clear view of the sky. These telescopes are not looking for new light, but for a specific swirl within the light we already have, a faint curl hidden within the CMB's glow. The search is incredibly difficult as this signal is buried under foreground interference from dust within our own galaxy. A future mission, Lightbird, is being designed to launch into space to escape this terrestrial noise, scanning the entire sky with unprecedented sensitivity to find this holy grail of cosmology. Success would open a window to energies so vast they are forever beyond the reach of any particle collider we could build. It would tell us directly about the physics that governed the universe in its first fleeting instance, revealing the engine that set the entire cosmic story in motion. The quiet expansion we measure today, the gentle push of dark energy, began with that primordial roar. Finding its ripples would connect our calm, stretching present directly to its violent, explosive birth, completing the most profound story ever told. But the steady expansion driven by a constant dark energy is not the only path the cosmos could take. A far more unsettling possibility exists in the realm of theory, a form of dark energy that does not remain constant, but instead grows more potent with every passing moment. Scientists call this hypothetical substance phantom energy. Its defining characteristic is a negative pressure so extreme that it violates certain classical energy conditions, making it a truly exotic component of the cosmos. If such an energy field were to exist, the quiet expansion we observe today would not remain quiet for long. It would slowly transform from a gentle, relentless push into an overwhelming, destructive force. This is the theoretical basis for one of the most dramatic end of the universe scenarios, the Big Rip. In this future, the repulsive force of phantom energy would intensify until it exceeds the strength of every fundamental force that holds reality together. The end would not come with a slow fade, but with a systematic and violent dissolution of the cosmos, all before time itself could reach a natural end. The process would begin on the largest scales. The phantom energy's strengthening grip would first overcome the gravitational bonds that hold immense galaxy clusters together. These vast cities of stars would be flung apart into the void. Next, the gravitational glue within individual galaxies would fail. The Milky Way, Andromeda, and all their countless stars would be torn asunder, each star set adrift on its own solitary trajectory. As the force continues to amplify, it would then target solar systems. The Sun's gravity would no longer be enough to hold its planets in orbit. Worlds would be ripped from their stars and cast into the expanding darkness. In the final, fleeting moments, the phantom energy would become stronger than the forces that bind matter itself. It would overcome the electromagnetic forces holding atoms together, tearing electrons from their nuclei. Then, in a final, fundamental cataclysm, it would exceed the strong nuclear force that binds protons and neutrons within an atomic nucleus. Every atom in what was once the universe would be explosively shredded into its most elementary particles. The very fabric of spacetime would be torn apart, marking a definitive and violent end to the cosmos. Currently, our most precise observations of the universe's expansion, from supernova and the cosmic microwave background, suggest that dark energy behaves like a simple, constant cosmological constant. These observational constraints place phantom energy firmly in the realm of the speculative. The data we have does not require such a dramatic component, and a constant dark energy remains the simplest and most supported model. Yet the door is not completely closed. The uncertainties in our measurements are small, but they exist. The faintest hint that the strength of dark energy might be increasing, even slightly, would shift the entire cosmic forecast from a long freeze to an eventual tear. The quiet expansion we measure is therefore a crucial diagnostic. Its precise behavior is the only way we can know if the universe is destined for a gentle end or a final, fundamental rupture, a question whose answer is written in the dark just beyond our current sight. The James Webb Space Telescope is peering into the cosmic dawn and seeing a universe that is strangely mature. Its infrared eyes, designed to capture the faint glow of the very first stars and galaxies, have found a surprising number of fully formed, massive galaxies shining in the darkness much earlier than anyone predicted. These galaxies appear too bright, too large, and too structured for their tender cosmic age. It is like opening a family photo album expecting to see pictures of toddlers, and instead finding portraits of young adults. This discovery presents a profound challenge to our established models of cosmic evolution. For the quiet expansion to have shaped the universe we see today, the initial seeds of galaxies, those quantum ripples from inflation, had to grow at a very specific, predictable rate, pulled together by dark matter's gravity. If galaxies assembled this quickly, it suggests that either the seeds were much larger than we thought, or the growth process was far more efficient in the early universe. This forces us to reconsider the entire timeline of structure formation. Was the quiet expansion driven by dark energy subtly different in those first moments, allowing for a more rapid clumping of matter? Or does this point to something entirely new about the nature of dark matter itself, perhaps that it interacts in ways we have not yet considered? These brilliant early galaxies are more than just cosmic curiosities. They are crucial data points in the story of the quiet expansion, offering a direct look at how the cosmos built its large-scale structure against the backdrop of an accelerating universe. Each unexpected galaxy is a clue, a piece of a puzzle that could force us to rewrite the opening chapters of our cosmic history and refine our understanding of the silent force that guides its ultimate fate. Even deeper than the ancient light of the cosmic microwave background lies a fossil from the universe's very first second. This is the cosmic neutrino background, a predicted sea of ghostly particles that has been flowing through the cosmos since it was a mere infant. While the CMB shows us the universe at 380,000 years old, this neutrino background would provide a snapshot from a time when the cosmos was only 1 second old, a period of unimaginable heat and density. Neutrinos are among the most elusive known particles, often called ghosts because they pass through almost everything. Trillions of them are streaming through your body every second, leaving no trace. This near-total lack of interaction is what has allowed this primordial sea to remain so pristine, a perfect time capsule from an era forever beyond the reach of light. Detecting this specific, low-energy background, however, is a monumental challenge. These primordial neutrinos have been stretched and cooled by the universe's expansion for nearly 14 billion years, and their incredibly faint signal is buried under a storm of neutrinos from the Sun, from nuclear reactors, and from other cosmic events. Catching one would be like trying to hear a single, specific whisper in a roaring hurricane. Yet, the scientific payoff for such a detection would be immeasurable. It would open a direct window to the conditions that existed just before the nuclear fusion processes that forged the universe's first light elements began. This would give us an entirely new set of data to understand the initial push of the quiet expansion, revealing how the infant universe behaved in its first breath, long before the cosmic dark energy we observe today began its work. This mathematical precision woven into the fabric of reality leads to a radical, almost haunting question. Could the quiet expansion and the unbreakable laws of physics be evidence that our universe is not a fundamental reality, but a sophisticated simulation? This is the core of the simulation hypothesis, a modern philosophical argument that suggests our cosmos might be a computational construct, an elaborate program running on a computer of unimaginable power in a higher-level reality. The idea, popularized by thinkers like Nick Bostrom, does not propose we are living in a video game in the trivial sense, but rather that an advanced civilization could eventually possess the processing capability to run vast numbers of detailed simulations of their own history. If such a civilization existed, the number of simulated minds could vastly outnumber the number of original biological minds. Therefore, statistically, it is more likely that we are among the simulated beings than the original ones. This argument rests on a chain of possibilities about technological advancement, but it finds curious support in the nature of the universe we observe. The laws of physics are profoundly mathematical. They are not just described by math, they appear to be written in it, operating on discrete, quantized levels that bear a striking resemblance to the binary code of a computer. The finite speed of light acts like a processing speed limit, a maximum frame rate for the simulation. The quantum weirdness of particles existing in multiple states until observed could be seen as a form of processing optimization, where the program only renders the details of reality when a conscious observer is looking. And then there is the apparent fine-tuning, the precise values of the fundamental constants, from the strength of gravity to the mass of an electron, seem perfectly calibrated to allow for the existence of stars, planets, and life. If any one of these values were slightly different, the universe would be a sterile void. From a simulation perspective, this fine-tuning is not a miraculous coincidence. It could simply be the result of intentional parameter setting by the programmers, who dialed in the conditions necessary for a complex and interesting cosmos to evolve. Of course, this hypothesis faces massive objections. It is arguably unscientific because it is currently untestable and unfalsifiable. There is no experiment we can run to prove we are not in a simulation, as any result we get could simply be part of the program. The sheer energy and computational power required to simulate an entire universe down to the quantum level is mind-boggling, perhaps physically impossible even for a super-advanced civilization. And if our reality is a simulation, what about the reality of the beings running it? Does that lead to an infinite regress of simulations within simulations? Yet, even as a speculative thought experiment, the simulation hypothesis forces a profound confrontation with the nature of our existence. It reframes the quiet expansion. Is the relentless stretching of space a fundamental law of a base reality, or is it merely a programmed parameter, a line of code designed to ensure the simulation runs smoothly and does not overload its memory? Are the cosmic mysteries we grapple with, like dark energy and the Hubble tension, not puzzles of fundamental physics, but perhaps glitches in the code, or features we are not yet meant to understand? This idea, for all its strangeness, pushes us to ask what reality truly is, and whether the silent rules governing the cosmos are eternal truths, or simply the local bylaws of a computational system we call home. This journey into the dark heart of the cosmos leads us to a profound and unsettling frontier, the role of the mind itself. Some interpretations of quantum physics present a universe where reality is not fixed until it is observed. In this view, a particle exists not in a single location, but as a cloud of potential, a wave of probability. It is only when a conscious observer makes a measurement that this wave function collapses and the particle takes a definite position. This idea seems to place consciousness at the very center of physical reality, suggesting that the universe requires a mind to bring it into being. The implications are staggering. Could the vast cosmic web, the quiet expansion, the very existence of spacetime be dependent on conscious observation? Does a galaxy in a distant, unobserved void exist only as a shimmer of possibility? These are captivating philosophical questions that touch on the nature of existence itself, yet for all their allure, they remain firmly in the realm of speculation. Mainstream physics finds no mechanism for consciousness to influence the cosmos on such a grand scale. The collapse of the wave function is generally seen as a physical process, not a mental one, occurring through interaction with any measuring device, not necessarily a conscious mind. This distinction is crucial. It keeps our exploration of the quiet expansion anchored in the world of testable hypotheses and empirical data. We measure the stretching of space through the dimming of supernova and the patterns in ancient light, tools that operate independently of human thought. While we can ponder the deep connection between the observer and the observed, our map of the cosmos is drawn from the light that reaches our telescopes, a silent signal from a reality that appears to exist on its own terms. This journey through the dark is not about what we wish to be true, but about listening to what the universe is telling us, one faint whisper at a time. Our quest to understand the quiet expansion ultimately brings us to the edge of a precipice, not just in space, but in knowledge itself. There are profound questions that the very tools of science may never be equipped to answer. What, for instance, happened before the Big Bang? The concept of a before might not even have any meaning if time itself began with that initial singularity. Our entire scientific method is built upon observation, testability, and repeatable evidence, but we are forever trapped within our cosmic horizon, unable to collect data from what lies beyond. The true, full extent of the entire universe is one of these ultimate mysteries. We can infer its likely vastness, but we can never measure it, never confirm its shape or its true contents. This transforms the unobservable universe from a simple region of space into a domain of fundamentally unanswerable questions. The quiet expansion is not merely hiding galaxies from our telescopes, it is actively concealing the answers to the deepest inquiries we can pose. This is an epistemological limit, a boundary built into the very rules of how we learn about reality. Science thrives on data that can, in principle, be gathered. But when the expansion of space ensures that crucial information is permanently carried away from us faster than light can travel, some truths may be forever locked away. The quiet expansion, then, is more than a physical process, it is a veil. It ensures that certain chapters of the cosmic story will remain forever unread, reminding us that the universe is under no obligation to make itself fully known to us. This cosmic perspective, written in the silent equations of expansion, carries a profound existential weight, learning that the universe is not only destined to end, but to fade into a cold, eternal equilibrium, forces a fundamental reevaluation of our own place within it. All human ambition, every work of art, every act of love and conflict plays out against a backdrop of eventual cosmic silence. The quiet expansion is not just a physical process, it is the context for our entire existence. How do we find meaning in a universe that appears indifferent to our presence, one that will ultimately outlast every memory and monument we create? This question is not new, but modern cosmology has given it a new and startling clarity. The universe does not offer us a grand purpose written in the stars. Instead, it presents us with a breathtaking freedom. The meaning of our brief moment in the sun is not something we discover out there in the dark, it is something we create right here. The knowledge of an eventual end does not negate our experiences, it intensifies them. It makes every moment of connection, every spark of curiosity, every effort to build a better world more precious, not less. This awareness also brings a profound responsibility. Our actions ripple not just through our own time, but into a future that, while finite, still stretches for billions of years ahead of us. We are the temporary custodians of a spark of consciousness in a vast and unknowable cosmos. This perspective can forge a powerful, planet-wide sense of solidarity. The divisions that seem so large to us here on Earth shrink into insignificance against the canvas of an expanding universe. We are all, every one of us, aboard a single, fragile world, adrift in a silent ocean of dark energy. This shared cosmic fate challenges us to look beyond our immediate horizons and consider the legacy we leave for the generations of minds that will follow, for as long as there are minds to wonder at the dark. The quiet expansion reminds us that our time is limited, and in that limitation we find not despair, but the very reason to make our fleeting story one of courage, compassion, and relentless curiosity. These cosmic questions lead us beyond the equations. The profound mystery of the quiet expansion cannot be contained within the language of physics alone. It spills over into the ancient domain of philosophy. The very nature of time, reality, and existence is now being probed by our telescopes, forcing a new dialogue between these two great fields of human inquiry. When a cosmologist calculates the eventual heat-death of the universe, they are also touching on a philosophical question about the meaning of a finite existence. When a philosopher ponders the nature of nothingness, they are grappling with the same quantum vacuum that physicists identify as the potential source of dark energy. This is not a one-way street. Philosophical frameworks help scientists recognize the assumptions buried within their own models. The cosmological principle, for instance, which assumes a uniform universe, is as much a philosophical stance about our place in the cosmos as it is a scientific tool. It guides where we look and how we interpret the data, reminding us that our perspective is inherently local and limited. Thinkers who bridge this gap, like the late philosopher of science Thomas Kuhn, help us see that our understanding of the cosmos progresses through paradigm shifts, where old models crack under the weight of new evidence, just as the Hubble tension is challenging our standard model today. Philosophy provides the conceptual tools to frame the right questions, especially when definitive answers are carried away by the expanding dark. It asks not just how the universe works, but why this particular set of laws exists, and what it means for a conscious mind to emerge within it, capable of observing its own eventual fate. This interdisciplinary conversation enriches the entire pursuit, transforming the quiet expansion from a mere physical process into a deep inquiry about the nature of reality itself, an inquiry where the journey of questioning is as vital as any destination we might one day reach. Our journey through the quiet expansion has brought us face to face with a cosmos of humbling scale and silent activity. We have traveled from the strict limits of our observable horizon to the speculative frontiers of multiverses and quantum vacuums, learning that the universe we see is a tiny, illuminated stage within an endless, dark theater. The true story of the cosmos is written not in the light of stars, but in the relentless, unseen stretching of the void itself, driven by a mysterious dark energy and shaped by an invisible architecture of dark matter. While the fundamental nature of these forces remains one of physics' greatest puzzles, the pursuit itself illuminates a profound truth about our place in existence. We are temporary witnesses to a grand cosmic narrative, a story whose final chapters are being written in a darkness we cannot penetrate. This is not a cause for despair, but an invitation to a deeper, more persistent wonder. The fact that we can ask these questions, that we can measure the faint echoes of creation and project the fate of all things, is a remarkable achievement of the human spirit. Let this exploration be a starting point for your own curiosity. We would love to hear which of these cosmic mysteries resonates most with you. Share your thoughts in the comments below, and if you want to continue exploring the edges of understanding, subscribe for more journeys into the unknown. Never stop looking up at the stars and wondering about the immense, quiet expansion happening just beyond their light.